We have two talks. The first talk is by Senthil from MIT, and he would be talking about superconductivity and quantum anomalous Hall effect.
Yeah, thank you, Subhro, and thanks to thanks to the organizers for inviting me to come here. It's a great honor to participate in this conference. Thank you to TVR. You've been a tremendous inspiration for me throughout my career, and happy birthday as well. So I want to say a few brief words about Professor Ramakrishnan's influence on me. Rajesh and I, we did undergraduate education in the late 80s, early 90s, by which time, the basics of localization theory was firmly in place, thanks to efforts by Professor TVR and various collaborators. And I grew up learning localization theory, and it was, as an undergrad, it was hard to grasp the concepts, but I realized that it's something that I certainly had to learn. It seemed to be all kinds of novel conclusions that were reached based on very elegant and simple arguments. And it looked mysterious at first sight, but I came to love it. And this had a very direct impact on me, on my postdoc research. And subsequently, I worked on localization as a postdoc. Read almost every paper you wrote on localization in the 70s and 80s. I only got to meet Professor Ramakrishnan in 1997 when I came to IISc at some point. And in the next 10 years, I had lots of discussions with him on a variety of topics in condensed matter physics, on high-TC superconductivity, disordered systems, quantum magnetism, just about everything. Got lots of insights and a lot of good advice. And on two topics that I very much cherish the insights and advice that I got from you. The first is on the joy of working at the interface of abstract theory and concrete experiments, which is something that's wonderful about our field of condensed matter physics. And the second is on various organizing decisions I was trying to make on living and working in India versus doing the same in the West. Got a lot of good perspective from talking to Professor Ramakrishnan. And for the young people in the room, I recommend a very nice article in the annual reviews of condensed matter physics that he wrote 2 years back, 3 years back, 10 years back. 9 years. But it's a same order of magnitude. But it's a very nice article, and I strongly urge you to read it. While reading it, I almost had the sense that I was speaking with him, listening to him one-on-one in person. All right, so let's get on with the talk. So the title of my talk is Superconductivity from the Fractional Quantum Hall effect. The work was done primarily with this wonderful student who's now a postdoc at Stanford, Zhengyan Shi, and a postdoc at Harvard, Carolyn Zhang, who came and hung out with us. What's with the name? Yeah, so he moved to the United States for high school and decided to give himself a Western name to make it easier for everybody. I know. But he was apparently fascinated by Darius, anyways, so let's start with superconductivity. And let me remind you of conventional wisdom on old folklore on superconductivity that's based on BCS theory, right? And this folklore, they're not theorems or anything, but these are, statements about superconductivity that are often true, but not always. The most basic statement is that superconductivity arises as an instability of a metal with a Fermi surface, right? That's BCS theory. And that we know is challenged, for instance, by the underdoped cuprates, where there's no simple Fermi surface that people can measure out of which the superconductivity emerges. So there are challenges, but by and large, this is how superconductivity happens in most systems. And we also learned that the superconductivity occurs through pairing time reversal related states. States are related to each other by time reversal. And that breaking time reversal is bad for superconductivity. Right? For instance, magnetic fields, everybody knows is bad for superconductivity. This is also challenged. There are, for instance, ferromagnetic superconductors that have existed for some time, uranium, rhodium, germanium, things like that. There's an interesting recent example of uranium tellurium-2, where superconductivity survives at up to 60 Tesla fields. Actually, it does something more bizarre. It first dies and then comes back. And most recently, the superconductivity seen in graphene stacks, 4, 5-layer, 6-layer graphene stacked in a particular way called the rhombohedral arrangement, where you again break time reversal and you have it's an orbital ferromagnet that becomes a superconductor. So there are counter examples to this statement, but by and large, this is the general expectation, right? That breaking time reversal is bad for superconductivity. Now, the excitations in a superconductor are Bogoliubov quasiparticles with an indefinite charge, because the condensate can absorb any amount of charge. And these are directly visible in experiments where we probe the excitations from the external world, say from photoemission or in electron tunneling, right? So that's the superconducting state, a one slide summary of standard story of superconductivity. Now, let me give you a summary of the standard story of the fractional quantum Hall effect. We take a two-dimensional electron system and subject it to a strong magnetic field to go into the quantum Hall regime. And of course, the magnetic field strongly breaks time reversal. And the excitations of quasiparticles with fractional charge and fractional statistics, we have anyons. And we can't create anyons in isolation in photoemission or in electron tunneling. They are weird objects. They can't be created locally from the external world because they have non-local statistical interactions with other anyons. And that's what it is, right? So that's the fractional quantum Hall effect. So the question is, why in the world would these two phenomena be related at all, right? So what possibly could be the relationship between these two? So there's an old idea due to Laughlin where he pointed out that you may get superconductivity in a mobile fluid of anyons. Okay? So this was proposed in the late 80s as a theory of superconductivity in the cuprates, and it's a failed theory of superconductivity in the cuprates. It was abandoned very early. By 1991, it was dead. And it goes under the name of anyon superconductivity. Okay? So the paper by Laughlin that introduced this idea had a very tantalizing title. So the title says the relationship between high TC superconductivity and the fractional quantum Hall effect. Now, these are two of the biggest discoveries in condensed matter physics in the 1980s. Right? And on the face of it, they should have nothing to do with each other. But Laughlin had a conception that maybe there was some sense in which they were really closely related phenomena. So there's the abstract of this paper, and the most important sentence is this, that particles carrying a fraction of an elementary quantum number attack one another by some force, which can lead to a new kind of superconductivity. Okay? And this was elaborated by many people in the next 2 or 3 years. Very influential was this paper by Chen, Wilczek, Witten, and Halperin, and several other papers. But they introduced a field theoretic way of thinking about whatever Laughlin was talking about. So there is some literature, right? Now, I should make a cautionary remark. Many of the statements in this old literature are wrong. That doesn't mean to say that the ideas are not interesting. They were certainly inspiring for us when we started working on this a couple of years back. So the inspiration comes from the old literature. but we can't just take over statements made in the old papers literally, right? There are incorrect statements, in fact, fundamentally incorrect statements. But we have 35 years of experience, so we have to revisit and rework through everything that what the physics is. So why was this idea discarded in the old days? So it was attempted as an application of the cuprates, and this mechanism for superconductivity requires strong breaking of time reversal symmetry, at least as conceived originally, right? And the cuprates, people looked for strong time reversal breaking and didn't find it. And so they said, okay, let's move on, let's do something else. Now, anyons, we know or realize in the fractional quantum Hall effect, right? So why not apply this idea of anyon superconductivity to the fractional quantum Hall effect? So there's another problem. The anyons are charged and they move in cyclotron orbits around in the magnetic field, right? If you create a charged excitation, it sees the magnetic field and it does this, right? So anyons have very little kinetic energy. The kinetic energy is suppressed, just like for electrons in a Landau level, as Ravindra mentioned in his talk. So you don't really have mobile anyons in the fractional quantum Hall state. So at low doping, if you dope this fractional quantum Hall state, you get localized anyons that gives you the width of the plateau. And as you increase the doping density further, eventually there is a phase transition to the next plateau, as Avik was talking about in his talk. So you see a plateau to plateau transition. So that's all that happens. Very interesting physics, as we learned in the last two talks, but it's not the physics of a fluid of mobile anyons. So, which brings me to the relatively modern era of 2 years back. So one of the big things that's happened in condensed matter physics in the last 2 years is the discovery of the fractional quantum Hall effect without a magnetic field in two-dimensional Moiré materials. So Moiré materials are 2D materials in which you take two slightly dissimilar materials, the monolayers of two slightly dissimilar things, stack them together to produce a long period Moiré pattern in which the electrons move. So these are lattice systems in which time reversal, which are microscopically time reversal invariant, and time reversal is broken spontaneously, and that enables the system to develop churn bands that are partially or fully occupied, and then you get an integer or fractional quantum Hall effect. So the mechanism for producing these churn bands is essentially what I've sketched here. So these Moiré systems, the electrons live in two different valleys, and these two valleys are related to each other by time reversal, right? So, for instance, there's one valley that's labeled by this label K. There's another valley labeled by K prime, and these two are related by time reversal. And you may have spin as an alive degree of freedom, and so then you have two bands in each valley. And since within a single valley, time reversal acts by taking one valley to the opposite valley, right? So within a single valley, there is no time reversal invariance. So the bands can have a churn number within a single valley, so long as the bands in the opposite valley have the opposite churn number, right? So this is the situation microscopically. Now, if with interactions you polarize the valley degree of freedom and perhaps the spin, if it's also there, then you may end up with, let's say, with one electron per unit cell, you may end up with a situation where there's an interaction generated splitting of these four bands so that only one of these four bands is occupied. Then you have an imbalanced churn number, and the system is then a churn insulator and has an integer quantum Hall effect at zero feed, right? And this has been seen in many experiments by now in the last few years. This integer quantum anomalous Hall effect in Moiré materials through precisely this mechanism. Now, if you tune the density so that you only partially fill this churn band, you might have hoped that you see a fractional quantum Hall effect in zero magnetic field. And that was a hope in the theory literature, but it was realized in experiments 2 years back, first in twisted molybdenum ditelluride, and shortly thereafter in multi-layer Moiré graphene, again rhombohedrally stacked Moiré graphene, just a few months later. So you have a couple of different systems in which this phenomenon is seen. So let me show you some data. This is an MOT2, and this data is from Shodong Chu. So this is a set of lattice filling of 2/3. There is no magnetic field here, so we're not talking about Landau level filling. We just have 2/3 electrons per unit cell on average, right? And at that filling, as function of field, if you measure either the RXX or RXY, you see this. There is hysteresis as a function of field, telling you that there's broken time reversal symmetry. But beyond the coercive field, the RXY gets quantized to be 3/2 h/e squared, which corresponds to a fractional Hall conductivity of 2/3 e squared over h. And likewise, this data are 3/5 and so on and so forth. In fact, amazingly enough, in both MOT2 and in rhombohedral graphene, the fractional quantum Hall states that are seen are only the Jane states. Right? So composite fermion theory works amazingly well for reasons that are somewhat mysterious. Right? It's not a Landau level after all. Right? The structure of the wave functions, everything is different, but still composite fermions work. So it's great. So this is the same kind of data is also seen in multi-layer rhombohedral graphene, by now with 4, 5, 6, 7 layers. So here, say in this picture, there's 5 layers of graphene that sheets stacked in a particular way, and and the experimentalist can apply an electric field perpendicular to the stack, so as to drive the conduction electrons far away from a HBN layer that's aligned with the topmost graphene layer. That's nearly aligned with the topmost graphene layer. Right? So there's a Moiré potential that's sitting here primarily, and the electrons are primarily sitting here at these displacement fields. And then you see pictures like this. So this is at mu equals 1, integer 1 electron per unit cell, Moiré unit cell. And you see, again, hysteresis, and then beyond the coercive field, quantization at h/e squared. And at 2/3, you see hysteresis and quantization at 3/2 h/e squared. Right? So this phenomenon of quantum Hall in zero field on a lattice system definitely exists. Right? Exists in experiments, not just in the world of theory. So there's a new setting for the fractional quantum Hall effect. Right? You have electrons on a lattice with lattice translation symmetry and time reversal symmetry, and microscopically, the electrons have block bands. Right? So this is a picture of the band structure calculated in the experimental paper, in Shodong Chu's paper. There is some band structure, right? For that, this is the electronic band structure. And time reversal is broken spontaneously. And we don't know this from experiments, but from all the numerics that people have done, we know that lattice translation is preserved in the observed fractional quantum Hall ground states. Right? We don't have a direct experimental proof, but we have pretty good numerical evidence that lattice translation is preserved. So you have a novel correlation-driven insulator. Oh, in exact diagonalization, you can try and look for charge density wave order or in DMRG, and people don't see it. Right? Right. No, it's domains, right? You're aligning the domains. Right? That's what hysteresis. Yeah, that's always the source of hysteresis. Right? Yeah, between the two. Yeah, no, that's right. Yeah. Yeah. So when you have domains, because these are churn domains, you'll have gapless modes in those at the domain walls. So people see all that. You can switch with the current, and there's all kinds of phenomena where you have multiple domains. But yeah. Okay, so what are the charged excitations of this state, right? Now, the charged excitations of any fractional quantum Hall state are determined almost entirely by the measured value of the Hall conductivity. You don't need to know anything else. They're universally determined by the presence of the fractional Hall conductivity. Old arguments by Laughlin and a lot of subsequent work. So for instance, so the prominent state seen in experiments in both systems is this 2/3 state. And for this 2/3 state, For instance, you have the Hall conductivity of 2/3 E squared over H implies that there are anyons with fractional charge 2e over 3 and with fractional statistics of 2 pi over 3. And a simple argument then also tells you that you must also have other anyons with charge e over 3 and with statistics minus pi over 3. Okay? So which anyon is cheaper depends on the microscopic model. It depends on detailed calculations. But these anyons are all available to the system as a matter of principle. Okay. Since Pierce asked, I put up a slide. So the deep infrared, if you go to very, very low energies, well below the gap to, this is a gap state of matter. So you go well below the gap to any excitations. You can ask, is there a continuum field theory description of the state that captures the universal properties of the ground state and the universal properties of any defects, excitations that you might create about the ground state? This is also very well known in the quantum Hall effect. It's a field theory known as Chern-Simons theory. It's only good for capturing universal topological features of the quantum Hall state. If you ask questions about energy gaps, this theory is not capable of addressing questions on what the energy gaps are, right? But for topological properties, this is fine. All the braiding, fusion, all the anyon data, right? The chiral central charge of the edge modes, the quantized thermal Hall conductivity, all of that data will be captured by this theory. Yeah, the fractional charge is measured. The fractional statistics is measured these days, right?
That was only there in the paper. I'm just trying to understand what more experimentally measured things come on.
No. You could ask that question. And typically the answer will be, there's nothing new that you will get from an effective theory compared to a full-blown microscopic theory, right? It's a bit, the right analogy, say in superconductivity, is to think about microscopic BCS versus Ginzburg-Landau, right? You don't expect Ginzburg-Landau to give you things that BCS cannot give you as a matter of principle. As a matter of practice, it's sometimes the effective theory can be much more efficient.
Or much more general.
It may be much more general, and here too it is much more general. After all, I'm going to apply this to these lattice fractional quantum Hall systems where the wave functions, the structure of the wave functions is completely different, right, from Landau levels. Is it holomorphic functions, this and that? Not clear, right? There's some special limits in which on the lattice that same structure will go through, but the experiments are not necessarily in that special limit of ideal Chern bands and things like that. Absolutely, yeah, that's right. So that again is constrained to a large extent by the measurement of the Hall conductivity that imposes some structure on the topological field theory. But beyond that, within that constraint, there are several choices. And oftentimes people assume that the simplest choice works. And simplest choice does work in maybe 95 out of 100 quantum Hall states that have been seen so far. In any case, this theory that I'm describing matches whatever is observed numerically, right? Well, numerically, you can calculate a lot more than you can measure in experiments, right, of the universal properties. And this theory works. It's known as the Chern-Simons theory. It's written in terms of an emergent U1 gauge field with this weird looking Lagrangian that people, at least the theorists in the room, have probably encountered. And there's a further term, which is an integer quantum Hall state response to an applied electromagnetic field. So really, you should think about this 2/3 state as an integer quantum Hall state plus a 1/3 Laughlin state of holes, right? So that's the right picture for what is seen at 2/3. And the anyon excitations, so this just describes the ground states of the system. Anyon excitations will be defects of this topological field theory introduced in the ground state, or you can think of it as objects that are sourced by massive fields that couple to these dynamical gauge fields, right? That are charged under this U1 gauge field. And there's two distinct kinds of anyons, and they're bound states with electrons, right? As I already described. So that's the theoretical framework to think about the universal properties of this ground state. Okay, since one of the new features about these states of the lattice is the presence of lattice translation symmetry, let's ask how lattice translation symmetry acts on the anyons. Okay? Now, on the microscopic electrons, lattice translation acts in the usual way. You take an electron from here, you move it to the next unit cell. That's it. Right? Now, in the low energy theory of the quantum Hall state, for instance, let me just focus on 2/3. We have a state, an incompressible insulating state at fractional filling of a lattice. Right? And obviously, that's not allowed within band theory. So it's a bit like some version of, it's a generalized version of a Mott insulator. It's much more exotic than a Mott insulator. It's a state that occurs at fractional filling, but it doesn't break lattice translation symmetry, right? I said that in the numerics, lattice translation is preserved. So how does the system manage to accommodate fractional filling while being a uniform ground state, right? And the answer is that it, of course, is that it develops it's because it has the fractional quantum Hall effect. So there are fractionally charged quasiparticles in the system. Now imagine constructing a state by taking, say, taking the 2/3 charged object and placing one such object in each unit cell of the lattice. So that's a way to make the system translationally invariant. That's not available unless you have fractional charges, right? But in the fractional quantum Hall state, you have fractional charges available, and then you can make a translation invariant state at fractional filling, right? So that's the picture of the ground state, that in each unit cell, there's an anion. Let me label this anion E, that's just sitting as a background charge in the ground state, right? I drew a square lattice because it's too lazy to draw a triangular lattice. These systems are actually triangular lattice systems. Now, if you take any other anion, an excited anion, and you translate it in the system, let's say translated one unit cell to the in the x direction, then in the y, then back in x, then back in y, right? When I do that, this anion A, it braids around with this background anion E. So these two anions have a braiding phase. It'll pick it up. This means that this A anion, when it hops around on the lattice, it's as though it's seeing some magnetic flux, though there's no external magnetic field. So again, the fancy way of saying it for theorists is that though lattice translations act in an ordinary way on the electrons, acts linearly is the technical term, it acts projectively on the anions. Right? One can think of this as fractional quantum numbers for lattice translation. Just like anions have fractional charge under the global U1, they also have fractional quantum numbers for lattice translations, right? And the projective phase is given precisely by this kind of picture, and it depends on the braiding phase between the anion A and the background anion E, right? Now, for the 2/3 state, this braiding phase is either 1/3 or 2/3, depending on which anion I have. So in either case, it's as though any anion that hops around in the system acquires a phase of 1/3 of 2 pi as it moves around an elementary plaquette, right? So it's as though it sees a magnetic flux. So the hopping structure of these anions, so this is like a familiar Hofstadter problem in condensed matter physics for particles hopping on a lattice with rational flux to each unit cell. So this means that these anions move in a reduced Brillouin zone of area 1/3 of the electron Brillouin zone. So if you go to 3 unit cells, then the anions don't pick up any phase when they hop, right? Let's say a 3/1 unit cell. So you have 3 degenerate species of anions that move in a reduced Brillouin zone, right? And generically, there's no reason for the bands of these anions to be flat. There's no symmetry that protects those bands to be flat. So anions will have a dispersion. Okay, and this story is confirmed in very recent microscopic calculations, both by Nicolas Regnault and by Islam Khalaf, just in the last few months. Yes, in India. Right. That's correct, yeah. The argument goes through. You can this is the kind of thing that can be made absolutely mathematically rigorous, has been made absolutely mathematically rigorous, right? For every topological quantum state with gapped anyons, this translation phase, this effect of translation is always going to be a phase which is determined by braiding with some other anyon. That statement can be made as precise as you want. People have proven theorems on this statement. Right? Yeah. Yeah, I can tell you in great detail. Oh, I see. Okay. So what do we have? We have a novel interaction-induced insulator, right? So this insulator is a fractional filling of a lattice and shows a quantum Hall effect in zero field. The excitations are anyons with fractional electric charge and a well-defined dispersion, right? Now, if we dope the fractional quantum anomalous Hall state, we'll then get charged anyons. We could get charged anyons at a non-zero density, but these anyons have kinetic energy, unlike in the usual fractional quantum Hall, and hence they can become mobile. They don't just have to localize, right? So this is what one may call anyonic quantum matter. We have an opportunity to realize a mobile fluid of anyons in this system by doping the fractional quantum anomalous Hall state. And perhaps this is the ideal setting for novel states such as this anyon-induced superconductivity. Okay? Of course, yeah, everything here is non-relativistic. Yeah, that's right. They're gapped as well, right? So near the threshold, it's always going to be quadratic. Okay, so why is this an interesting question to consider? Let me briefly flash a couple of slides, and then I want to talk about the results before Subhro kicks me out. So the first motivation is that doped Mott insulators are interesting, right? All of the cuprate phenomena happen when Mott and Landau fight with each other, right? So here we have a new kind of correlated insulator, and since Laughlin, of course, developed the first theory of the fractional quantum Hall, but the states that are seen are all Jane states. So I decided to put Jayendra's picture as well. So you can now ask the question, if Laughlin and Jane fight with Landau, what's going to happen in the middle, right? Yeah, so I think that's a fun question to contemplate, right? And the other reason to think about this, I grew up spending a lot of time thinking about spin liquids and things like that. And you tell experimentalists, Hide Takagi-san is here, tell him to dope ruthenium trichloride or get some iridate. It's really hard, right? Takagi-san will tell me iridate doesn't want to leave the 4+ state, right? Things like that. But here, doping is routinely done with a gate voltage, right? That's one of the big selling points. These are the first papers on the subject. They already show phase diagrams as a function of doping, right? So it's routinely done in experiments, right? So we should be thinking about what happens when you dope these systems. So how should we study this problem theoretically, right? One option is to do numerics on microscopic models, and it's very hard. The models are not easy to study, and the numerical methods are also not easy. So we're trying to do some of this, but the first thing to do is something simpler, which is to use an effective field theory of the fractional quantum anomalous Hall state and understand within that effective field theory what the dope state can do. So it's an illustration. If you take the problem of doping charged 2/3 anyons into the 2/3 fractional quantum Hall state, you take the Chern-Simons theory that I wrote down earlier, and you couple it to gap matter fields. In this case, these are fermion fields. And there are 3 species of them because of what I explained about lattice translation. And you can work with this theory and analyze what happens within the scope of this field theory. Okay? Let me just show you the results that we get. At 2/3 filling, when you dope the 2/3 anyon, you end up with a superconductor which is smoothly connected to a BCS superconductor. Right? It's a charge 2 superconductor. The only slight non-triviality of it, apart from the mechanism, is that it's a topological superconductor. It has 4 Majorana modes going in one direction at the boundary. Right? So there's a realization of superconductivity in a charged anion fluid, and it's strongly time reversal broken, and there's no normal state Fermi surface. Okay? Now, it turns out you don't need to get a superconductor. You can also get a metal, and that's what happens if you dope the charge 1/3 anion. So then you just end up with a metal, and the most natural state. Am I done? Can I take a couple more minutes? Yeah. It's just an ordinary metal coexisting with a charge density wave order that triples the size of the unit cell. So it's not a given that you're going to get superconductivity, right? It really depends on what happens. So I'll just give you some intuition for why you get superconductivity when you dope the charge 2/3 anion. And then I want to come back to experiments and show you a couple of things in the experiments, right? So if you have a fluid of charge 2/3 anions, you can ask, what is the smallest charge that can be added locally from the external world, say by tunneling? You can't tunnel a charge 2/3 anion because the external world doesn't have those objects, right? You can't tunnel 2 of those because that's a charge 4/3 anion. But 3 of those is a charge 2 particle, and it turns out it doesn't braid with anything. So you can tunnel 3 of these charge 2/3 anions from the external world, but that's just a Cooper pair. Right? So you can tunnel Cooper pairs from the external world, but there's no way to tunnel single electrons from the external world at low energies into this fluid. So if you're an STM person, you can tunnel with you can't tunnel with a metallic tip, but you can tunnel with a superconducting tip, right? So which means you can think about this as a fluid of Cooper pairs at finite density. So then perhaps it's not crazy to find a superconductor, right? So that's some intuition. So before I finish, let me tell you about an experiment that showed up very recently, just a few months back. So this is a signature. I think this is really exciting, so I want to finish with this. The signature of superconductivity near the 2/3 state in twisted MOT2. This is the phase diagram. Blue means low or XX, and the 2/3 state is indicated here. And right next to it, there's a tiny region of blue, and that's a superconductor. That's a signature. That's a claimed superconductor. So it's more meaningful maybe to look at these line cuts. Rho XX is a function of the doping, the filling, and this is the rho XX minimum corresponding to the fractional quantum Hall state at 2/3 filling, and this is the rho XX minimum corresponding to the claimed superconductor, right? Now, the thing to recognize is that both the quantum Hall and the superconductor are dissipationless states. They have 0 rho XX, right? So the real question is, what's rho XY doing? And of course, in the quantum Hall, the rho XY is large, in the superconductor, it's small. In the claimed superconductor, it's small, right? So this is promising as realization of superconductor next to this quantum Hall state. And can we declare victory, right? So I don't think we can declare victory yet. A lot more experiments are needed. So in particular, there is a really important question as to whether the normal state out of which the superconductor emerges has a carrier density, a mobile carrier density, given by 1 minus nu, the deviation from integer, whether it's given by the deviation from 2/3, right? If it's the former, then the right picture is not that of doping the quantum Hall state, so doping the integer quantum Hall state instead, and having a Fermi surface, which then has an instability. So the anionic mechanism requires a small carrier density. Again, similar issues, people who work on cuprates know these issues very well. So I don't know the answer, but a couple of weeks back, I was looking at the data again, and I noticed something that's very, very interesting and very encouraging. So there's the plot of rho XX as a function of temperature. And as you go from green to black, you're going away from nu equals 1, right? And you see that the normal state resistance increases as you go away from nu equals 1 towards nu equals 2/3. So if the picture is that of a large Fermi surface obtained by doping nu equals 1 state, then you're increasing the carrier concentration as you go up here, but nevertheless, the resistance is increasing, right? It's a lot easier to understand if the carrier concentration is set by the deviation from 2/3, So you have a small carrier density. So then, of course, in this small change of parameters, you're going to get a big change of resistivity. So maybe I should just stop here. Have a couple of more slides, but let me just stop with a conclusion. And thanks for your attention.
Thank you, Senthil. So a couple of quick questions.
So I'm just trying to understand this intuitively. So the boson that Bose condenses is charged to the object.
Yeah, that's the order parameter. The picture is not that of coming out of the fractional quantum Hall state.
Yeah.
The mechanism is not Bose condensation. It's the anionic mechanism.
But at the end
But
of the
at the end of the day, the order parameter is just a charge to order parameter.
So here you're saying that it's somehow 6 charge 1/3 quasiparticles combined to form this boson to Bose condense. So is there a
Right, no. So in terms of mechanism,
yeah?
it's not correct that 6 of the 1/3 or 3 of the 2/3 have just Bose condensed. Because if they did, you won't kill the anyons, right? But the state that I'm describing has no anyons left, right? So the mechanism is different from just Bose condensation of the charge 2 object. There's a different mechanism, but at the end of the day, the superconductor that you get is characterized by a charge 2 order parameter. Though how it got there is different from the standard Bose condensation story.
Okay.
So you showed that experimental data at the end there. Is there, what is expected about the finite temperature transition? So maybe you said it there.
Yeah, I didn't say it. So I'll tell you what's expected. It's actually really
It
cool.
doesn't look like a thermal transition is happening.
Very good. That's because I had an explanation for that in the slides that I skipped. I'll just say it, since you asked, I'll just tell you what is expected theoretically within this anion doping story. So when you work it out, because of disorder, it turns out that the crucial observation is that an anion in the fractional quantum Hall state, when you dope it to get a superconductor, it transmutes into a vortex. Okay, and then this is the crucial slide really. When you first dope the 2/3 fractional quantum Hall state, you're going to get localized 2/3 anyons, randomly sprinkled, and that's the width of the plateau. Right? Now, as you increase the density, charge density further, the next anyons that go in, they form a mobile component that sees these localized anyons. But these localized anyons transmute into vortices, right? Of either orientation, and the fluxes can be plus or minus. So what you get is a vortex glass state with randomly pinned vortices, but without any external magnetic field. And a vortex glass was discussed in the 1980s, late 1980s, and it's known that there is no finite T BKT transition. There's always creep of vortices. So here, of course, as you correctly pointed out, this doesn't at all look like BKT. Now, I don't know whether it's the explanation is the vortex glass or it's something that various experimentalists in the room will tell me is due to a bad contact, not good current paths between the contacts. These samples, I don't know the mobility, but these samples are they're the best MOT2 samples anyone has made. He sees quantum oscillations in these samples. No one has ever seen that before. Right? So the sample quality is really good. I don't know about the contacts. Abhay will probably tell me that I should never trust any transport experiment unless he does it on transport and TMDs. Is that correct? The contact resistance can be very big, right?
Let me ask you a question.
Yeah.
The thing one could do is to measure the dispersion of these anyons. How would one do that?
Yeah, I've wondered about it and I don't have a good idea. I'll tell you the best I've come up with so far. It's to do STM. No, really. As you know very well, and perhaps the people in the audience, Mohit knows this very well, in cuprates, people do this quasiparticle interference to pull out their Bogoliubov quasiparticle dispersion, at least aspects of its dispersion. Here, that may be the best bet because if I have an impurity, right, and I try to tunnel charge into it, the tunneling density of states will be affected by the impurity can scatter anyons from one momentum to the other, right? So I go near threshold and I look at the STM spectrum near the onset of conductance, and I look at the tunneling interference, and that may have some information on the spectrum. But as I said, I don't think it's a great idea, but it's the best I've been able to come up with so far. There's room for some creative thinking here. So if anyone has ideas, tell about.
Okay.
Yeah,
The
so-
last question, Suraj.
So more on the theory side. So you showed this lattice with this anion sitting there.
Yeah.
So the modern understanding of like gap versus gapless is through LSM, right?
Yeah.
So
yeah.
so how do you so how does the LSM argument go through?
Yeah, it's LSM that forces that structure. LSM stands for Lipschultz matters, right? That's what I mean by filling constraints,
Right.
right? So, so LSM allows the state to occur precisely because it has fractionalization. Again, the modern version of Lipschultz matters is to think, at least one version is to think in terms of what happens when you thread a 2pi flux,
Right.
and ask how much momentum you transfer.
Yeah.
Right? Here, the state, because it's topologically ordered, it has degenerate ground states on the torus. So when you thread 2pi flux, you go from one ground state to the other. And the difference in momentum of these two different degenerate ground states in the torus compensates for the missing momentum due to fractional charge. So everything works out wonderfully.
So can you access gapless states by with the different filling fraction? So it gives you constraints on the filling fraction. And based on that, whether you can have a gapless state or it has to be a gap state with a topological order.
Yeah, that's right. So here you can certainly have a gapless state. You can have a metal, right?
Right.
You can have a Fermi gas. But if it's gapped, then it must have topological order.
Okay.
And the topological order is, so this state that I'm describing, the 2/3 Jane state, is an allowed state.
Okay.
Okay, let's stop. Let's thank Senthil once more.